Okay, so the first part of the talk really is kind of a review of continuous time Markov chains. Part of the motivation is that looking through the list of speakers and abstracts, I know there will be people who take very different approaches to studying continuous time Markov chains coming up on this, and so the first thing I want to say is a little bit about the relationship among these different approaches, which in some sense are basically all equivalent, but different people do different things with that. And then the second part of the talk, I tend to run over, but I'll try to stop. The second part of the talk, I want to illustrate some of the asymptotics that one does on Markov chains to derive some of the different kinds of reduced models that I know people will be talking about later in the week. So my favorite way of describing a continuous time Markov chain, and there's the reference to the book up there, is to just simply, one of the distinctions that has been clear to me over the years is that mathematicians seem to think about stochastic processes physically, and physicists, which extends to chemical physicists, tend to think about stochastic processes mathematically. What do I mean by that? Mathematicians tend to look at stochastic processes in terms of sample paths. What do the sample paths look like? Well, continuous time Markov chain, the sample paths, they're constant except for various kinds of jumps. And so you describe your process in terms of the jumps that it takes, okay? And in this case, I'm assuming I've got a process that only has, say, m different kinds of jumps. In other words, since this is a chemical networks meeting, there are m chemical reactions in the model. And each chemical reaction, it consumes certain molecules and it produces certain molecules. So it produces a change in the numbers of molecules of the different chemical species. And the zetas are the net result of one reaction. Zeta k is the net result of one move by the kth reaction. And then it just simply is bookkeeping to say that the vector x of t, which gives the vector of the numbers of molecules of each of the chemical species, it's what you started with, plus Rk is the number of times that the reaction, the kth reaction, has gone forward. So you multiply that by zeta k, that's the total change in the numbers of molecules that have been that resulted from the kth reaction. You sum over k, and this is just a bookkeeping arrangement. Okay? So that's what I mean by the sample path is just this expression here. It's constant except for jumps of different net reaction results, or the jump sizes. When I say that the physicists or the chemical physicists tend to look at stochastic processes mathematically, I mean that basically if you look back through the historical literature, they have, in the physicists, well, say for diffusion processes, have studied Fokker-Planck equations, and for the Markov chain models that we're going to be talking about here, they've looked primarily at what in the chemical physics literature is known as the master equation, and in the mathematical literature is known as the Kolmogorov-Forward equation. So differential equations versus looking at things like this. Okay? I'm a mathematician. My preference runs in this direction, and so one of the things I want to do is to try to indicate how you can see sort of systematically that this approach is basically equivalent to all these other approaches. So, all right, so this is just the x of t equal x of 0 is just a bookkeeping operation. If we're talking about continuous time Markov chains, the intuitive idea is you have a jump intensity. The probability that you see a jump according to zeta k, that's the same as saying the probability that rk jumps by 1. And the intensity, the intuitive idea of the intensity is that this should be approximately lambda k of function of the current state times delta t, okay? Now, my claim is that this intuitive idea of intensity translates very nicely into an identity that says that rk of t should be a unit Poisson process yk evaluated at the integral of the lambda k. Now, the primary defining property of a unit Poisson process is that if you take a little interval of time delta u and you ask what happened, what's the probability of anything interesting happening in the next little interval of time, that is, given everything that's happened in the past, that is approximately just u, approximately just delta u, okay? So that's the basic property of a Poisson process, of a unit Poisson process. Same idea, the probability of seeing a jump in this thing in the next little interval of time delta u is essentially delta u. Okay, well, if I look at this object here, if I increase t by an amount delta t, that integral will increase by approximately delta t times lambda k. This is a unit Poisson process, so the probability of seeing a jump in rk is approximately delta times yk, okay? So that's the intuitive idea that leads to this final equation, which is a simple stochastic equation for a standard continuous time Markov chain, okay? And so this is the point where I'm going to start, and somehow we have to see how that relates to all the other ways that people formulate continuous time Markov chains. Okay, so first thing we want to look at is what I'll call the martingale properties. If you don't know what a martingale is, don't worry about it. We're not really going to use them, except, well, I'll tell you the one thing you need to know about martingales in a minute. If I take my RL, and remember K rather than L, I get my RKs by substituting in this integral into the unit Poisson process. Okay, and property of the unit Poisson process, among other things, is that the expectation of y of u is just u. Okay, so when I take this and I center it, I subtract off the integral that's inside. Okay, well, this integral isn't deterministic, but it's still the case that the expectation of that will be 0. Okay, centrally centered by something that's like an expectation. In fact, it's more than that. Okay, if I take my counting my RL and I subtract off this integral, which is just gives me this object is something called a martingale. Okay, and the primary fact about martingales you need to know is that the expectation of that is indeed 0. Okay? Now I'm going to play with this a little bit. I'm going to look at f of x of t, and I'm going to write f of x of 0. If x jumps by zeta L, okay, the change in f of x is just this difference here. And this is sort of an integral. You've got the RL as a counting process. It just jumps by +1. So this counts, the RL essentially counts the number of jumps of this type. And so this identity is just a more complicated way of writing my bookkeeping. But now if I center this, using this definition of RL, if I center this part is still a martingale, which means it has expectation 0, okay? And this is what's left over, okay? So if I take this and subtract it from the other side and take this sum and subtract it from the other side, that means that expression becomes a martingale. So if I define AF essentially to be the sum of the lambda L times f of x plus zeta L minus f of x, okay? This is the expression that you get after you move everything to the left-hand side. That's equal to this, and that is a martingale, okay? And in the mathematical literature, the A here is referred to as being the generator of the process, okay? Now, one thing I should have mentioned back here is that this martingale property, the fact that these RL of t's minus these integral of zeta L's are martingales, that in the hands of Jean-Jacques and others is another way of characterizing the continuous time Markov chain. All right, so we have one way. My claim is that the solution of this equation here gives you a continuous time Markov chain with the right intensities. Classically, even before the equations came along, Jacques and others characterized continuous time Markov chains in more general counting processes by the requirement that these things be martingales, okay? That translates immediately into the fact that these things are martingales. And one of the standard approaches for general Markov processes is to look at objects like this, where A is some linear operator, and to require that these expressions all be martingales. That's become one of the standard ways of characterizing general Markov processes, okay? And of course, all of this goes back. Each of these approaches is equivalent. The stochastic equation basically gives you the chain, the solution of what would be called a martingale problem, the requirement that these objects be martingales, that essentially characterizes the chain. And now I want to use, I said, the one fact you really need to know about martingales is that the expectation of this object here should be 0. Okay, so let's see how we can use that. All right, if the expectation of this is 0, then I can rearrange things, and after I've taken the expectation, I get this identity up here. It says the expectation of f of x of t is equal to the expectation of f of x of 0 plus the integral of the expectation of a. But now if I go back and I plug in f of x just to be the indicator of y, okay, the identity becomes this, all right, which now a different group in the audience will recognize is really just the master equation or the forward equation for the Markov chain. So the solutions of the stochastic equation have these martingale properties, properties with these martingale processes with these martingale properties have these expectations, and that leads to the master equation, okay? And then we have a theorem that says essentially it goes back, okay? It says here if you read this is nu y as my initial distribution. Okay, so we have a probability distribution on ZD, and we let x of 0 satisfy probability of x of 0 equal y equal to y. The system of differential equations, this thing here, the master equations, system of differential equations has a unique solution with full probability, okay, if and only if the solution of the stochastic equation satisfies, I didn't point out, I said what tau infinity was, but I didn't mention it. Tau I is the time of the ith jump of the process, and tau infinity is the limit of the tau i's, okay, which need not be finite, okay. You may have processes that blow up in finite time, but if it is, and if tau infinity, I mean, need not be infinite, because you may have processes that blow up in finite time, but if tau infinity is infinite, then there is a unique solution to the master equation, okay, and with the property that the sum of the py of t's is identically equal to 1, and conversely, if you have a unique solution to the master equation and the sum of the probabilities is equal to 1, then you have a solution of the stochastic equation that does not blow up, okay? So that's the equivalence of these various approaches. And just to relate that, I've already been using the chemical terminology. So you know, this is the standard sort of chemical network notation. So if nu k is the vector, if nu k is the vector, well, if the nu ik is the number of molecules of species I that's consumed by the K3, by one move of the K3 action, and nu k prime is the number of molecules, nu ik prime is the number of molecules of I produced, then nu k prime minus nu k is the change, so this is my zeta k, okay? And the simple Markov chain model for this chemical network is just given by this equation here. Of course, we need to, if you need a model, you need to specify the lambda k, and I think this is common to everybody here. If you want to apply the stochastic law of mass action, then binary reactions, the lambda k should be proportional to the product of the number of molecules. Unary reactions, the lambda k should simply be proportional to the number of the molecules that are consumed in that unary reaction, okay? The rates depend upon what's consumed, right? Not what's produced, okay? All right, so where do we go from here? Of course, my entry into this business was, this was about the 50th anniversary of this result, so you know, before most of you were born, okay? Before all of you were born. So, okay, so here's the game. You know, of course, in about 1965, chemical reactions involve gigantic numbers of molecules. You know, that's changed. Today, there, you know, may only be a few, but in 1965, chemical reactions involved something on the order of 10 to the 23rd molecules, okay? And so if you counted the number of molecules and you let n naught be Avogadro's number times the volume in liters of the reaction system, you get Ci is the chemical concentration, okay? And if you normalize the stochastic equation I've been talking about by n naught, okay, and there's a nice story you tell why the reaction rate should be multiples of n naught. All right, you end up getting an expression like this, and the first thing you need to know, you know, this is just the law of large numbers of the Poisson process. For some reason I didn't write that down over there. You know, y of nu divided by n is approximately u, Okay? So that means I should be able to essentially throw all this stuff away if n naught's really big. And that leaves me with essentially an equation that looks like this. And if you think about it a bit, this is the classical law of mass action that I learned in freshman chemistry, okay? Some of you may have learned it in freshman chemistry as well, okay? So that was nice. Got me out of Stanford at any rate. Then the next thing, since a natural way to think about this is, y of nu over n as you let n go to infinity actually converges to u. That's just the law of large numbers. If there's a law of large numbers, there ought to be a central limit theorem. And so step 2 in this is you've got this limiting differential equation. I've now called it f of x, okay? F of x is defined somewhere, I think. Yeah, f of x is defined here. It's the sum of the rates times the zeta k's, which is basically what's left after you cancel the Poisson processes. You sum over k, and you're summing the rates times the zeta k, okay? All right, so you've got a solution of the differential equations, the law of mass action. You center xn by, xn is the equation normalized by n. You center xn by x of t, multiply by the square root of n, and you work your way through this equation, and lo and behold, with this scaling, you end up with this expression here. And I did write this on the blackboard, I think. That's essentially the unit Poisson process at time nu minus nu divided by the square root of n. Along with the law of large numbers for the Poisson process, there's something called the functional central limit theorem, which says that this object here is approximately a Brownian motion, okay? So that means you no longer throw away the wk. In this normalization, wk tilde is the wk. Did I say that someplace? No, I didn't. Wk tilde is w tilde of u is just y of u minus u, okay? But with this normalization, this 1 over root n wk tilde n of something is essentially a Brownian motion at something, all right? So this expression here, this wkn, which is the 1 over root n yk tilde, I've got this identity. As n goes to infinity, this converges to a Brownian motion. You do a little Taylor series expansion of this, and you get an identity here that's good up to order of 1 over root n, and this all converges very nicely to the un converges to the solution of this equation, and this is now, I think, more frequently called the linear noise approximation. In the old days in the physics literature, it was called the Van Kampen approximation. And in particular, by approximation, xn is the normalized, is the state divided by n, okay? And that's approximately the deterministic limit plus this little Gaussian perturbation, okay? So okay, I guess I've got one more in. Whoa! Okay, I guess I have one more in here, and that is, how do you by going through basically the same kinds of arguments, you derive what would be called, I would call the diffusion approximation, and for some reasons that I won't go into, in the good old days, the physicists called it the nonlinear diffusion approximation. As I guess to distinguish from the linear noise thing. But it's also, I think, more frequently now simply called the Langevin approximation. Okay, that's history, all right? Now, there are, fast forward about 40 years, or 35 or something like that, and all of a sudden, chemical reactions started involving small numbers of molecules. Okay? Well, small numbers of molecules of some chemical species and large numbers of molecules of other chemical species. So these classical limit theorems that sort of assume that everything was of the same order, they don't help anymore, okay? And what I hope to do in the next, I got 20 minutes, right? Okay, what I hope to do in the next 20 minutes is just to give the simplest examples I could think of the different kinds of issues that come up in that, in this much more recent setting. So here's one example. Okay, it's there are, I don't know, count them, 4 chemical species here. We're producing, if you want to think of these as enzymes, we're producing substrate out of nothing, and then there's some interaction between the substrate and perhaps some enzyme which produces a product. And so we have this, and here is the, this gets, somebody once accused me of having ugly slides, which is true. And you kind of have to parse this, but this is our stochastic model for this chemical network, assuming that there are large numbers of molecules of S and P, so we scale everything by n, okay? And again, if you actually have real chemical reactions, then you have to start making some guesses about what the rate constants are in order for all of this to make sense. But then, the enzymes, they're, only small numbers of these. So we keep the enzymes. These are still integer values. There's no normalization. These are integer values. And for large values of n, these things are approximately continuous. Okay? Exactly the same argument that I used before. As n goes to infinity, you can throw the 1 over n y2n away, okay? So, you've got to work a little bit to make this rigorous, but it's not very hard to make this rigorous. I don't think you're going to make a mistake, just using your intuition on this kind of a representation. So you get convergence where the first 2 components here are going to be essentially solutions of differential equations, except they're not really, because they've got these stochastic inputs, all right? And so you've got a couple of continuous variables and a couple of discrete variables. And in the literature, I think the chemical physics literature, the literature of this crowd, these things are called hybrid models, okay? If you go back, not 50 years, but maybe 25, I think, you'll find the literature, they're called piecewise deterministic. Mark Davis of Imperial was one of the, in fact, he's wrote a book on it, a book actually probably might very well be worth reading for people that are interested in these things. Okay, at any rate, so that's sort of example 1. In this new world we live in which at least some chemical species are in small numbers, okay? We see that there are multiple scales. That's a term that gets used frequently now. In this case, in this model, I had multiple, call them spatial scales, because I had just had different normalizations of the numbers of molecules of each of the chemical species involved. Okay, needless to say, this can become a lot more complicated, because in fact, not only do you have models in which you have finite and large numbers, but large can mean multiple different things depending upon the chemical system. 10,000 from the point of view of the law of large numbers, 10,000 is pretty big. Okay, so, but it's not as big as 1 million, and it's certainly not as big as 10 to the 23rd, okay? So, these scaling arguments can become much more complicated. Okay, but also, not only do you have in some sense different scales for the numbers of molecules, but it comes out, at least in the models that I've looked at, and this is a list of people that have been involved in. See, we've gotten a little more modern than 50 years ago now. People that have looked at these things with me, the models that we've looked at have frequently had large variation in the rate constants. So you've got large variation in the numbers of molecules, large variation in the rate constants. So not only do you end up with sort of different normalizations for the numbers of molecules, you also end up dealing with what are basically different time scales, okay? And the simplest example that I know of for this is simply the classical simple model of an enzyme reaction, which is, ends up giving Michaelis-Menten. Okay, so A plus E, works back and forth to, okay, A is the substrate, E is the enzymes, and AE is the enzyme-substrate complex, and so you get this kind of production of the complex and then ultimately production of a product. In this representation, the E's are preserved in terms of the fact that the number of complexes plus the number of free enzymes is a constant, okay? And we'll call that constant M, and M is finite and it stays finite, okay? And so here again is the stochastic, here again is this, well, okay, missed the wrong. Here's the equation for the numbers of substrates. They get eaten up in the formation of the complexes, and they are also produced at, whoops, I'm missing a reaction here. Okay. All right, well, let's forget the reversibility here. I'm missing a, oh, okay, no, I guess this is right. This is the substrates are consumed in the formation of the complexes. The complexes break down, and so these things reform. Yeah, no, that's right. And these things reform. On the other hand, the complexes, they're in terms of the number of free enzymes, they get eaten up in the formation of complexes. They get returned if one of the complexes dissociates, and they get returned when the product is produced, okay? And we're going to look at this equation here, and, not surprisingly, I want n to go to infinity. That again means we can kill off the 1 over n y1n, okay? And the 1 over n y2n, all right? But we started getting into trouble here because as n goes to infinity, here's an n, there's no normalization here. This process here is jumping up like crazy, and this process here is jumping, well, we're jumping down. Okay, there's a minus sign here. So this is consuming XE very rapidly, but this is producing XE very rapidly. So the number of free enzymes is varying, all the way from 0 to m with great rapidity. So XE doesn't converge to anything, right? So the game we're going to play, and this is not the simplest way to prove my theorem, but it's not my theorem, but in any case, it's not the simplest way to prove the limit theorem. But in more complex models, it turns out that the easiest way to deal with more complex models than this one is to introduce a measure, okay? So what does this say? I'm integrating from 0 to t. This is the indicator function of some set C. This will be a subset of the integers from 1 to m, okay? So this is 1 if the number of free enzymes is in C and it's 0 otherwise, all right? So this is, nice and additive. So this is a measure in, space cross time, all right? And, for the mathematicians, it's living. It's a measure with total mass on the interval 0 to t. It has total mass t, okay? And it's living on a compact set, and there's a theorem that says, in some sense, this sequence of measures ends up going to infinity. This sequence of measures is relatively compact. So this thing, you can pick out, converted in the compactness ideas, you can at least pick out a subsequence along which this sequence of measures converges. Okay? So let's see what we have. Let's see what happens to this equation for xa if we assume that we've got this sequence of measures gamma n. Well, first we want to write xn and we want to put in gamma n. Okay? We've integrated k against. We've replaced xe here essentially by the integral against this measure, okay? So this measure is a measure in space and time, okay? So this is actually an identity. But then if you let this measure, if you let n go to infinity and you pick a convergent subsequence, the gamma n has to converge, along a subsequence, the gamma n will converge to something. And the time marginal of this measure is just ds, is just Lebesgue measure, okay? So along a convergent subsequence, this is my limiting equation. I get a limit, at least along a subsequence, okay? Where this mu s is something, and if I want to complete this argument, what I need to do is identify what the mu s is, okay? All right, so you play games now. Here comes the generator that I had before. All right, and we have this identity here with the different counting processes. A little bit of extra work, and you discover that expression, along the same subsequence, you can figure out what the limit of this identity is. Well, let's see, I should first point out that what you do here is you divide this identity through by n, and you end up with an expression that looks like this, okay? Well, if you mess with that, this is the sum of these integrals is 0. So if I differentiate, okay, the inside must be 0 at least most of the time. So my mu s must satisfy an equation like this, and then you have to stare at that for a while, and you realize that mu s has to be the stationary distribution for an extremely simple Markov chain, or chemical reaction. A1 goes to A2 and A2 goes back to A1. Okay, so it's a stationary distribution for a simple Markov chain like that. Therefore, it has to be binomial, and you can figure out what the PS is, and it's this kind of an expression here, and that should begin to look familiar. If I take that and I plug it back into this identity, surprise, surprise, what you end up with is this differential equation here, which at least all the chemists in the room will recognize. This is the classical Michaelis-Menten, okay? This result was proved again a long time ago by Tom Darden using very different, I mean, this derivation of Michaelis-Menten starting with the Markov chain model rather than the ordinary differential equations. This was done a long time ago using other methods by Tom Darden. Okay, what I said way back when, I've still got 5 minutes. What I said way back then is you've got this is a law of large numbers, right? I started with this stochastic thing and I got something that's deterministic. So law of large numbers, there's got to be a central limit theorem. Okay, so well, let's see. All we have to do is take our normalized process xn and subtract off the differential. Did I skip something here? No. Okay. All we have to do is take our normalized identity here, and we want to center it by the solution. I changed notation, unfortunately. I want to center it by, this is the deterministic Michaelis-Menten equation. I want to center xan by xa. I want to scale it. Good guess would be by square root of n. And I want to prove the limit. Okay. So let's see what happens here. First thing I want to do is I'm going to center the y1 and y2 by the integrals that are inside. And the centered parts, this expression here, here's that term again. This expression here is a martingale. So let's just call that mn1 so the equations fit on the screen. So here is the mn1. So after I've just transformed this, so this is the equation that I get left. And again, what I want to do is subtract this from this. But if you remember what happened before, is this was just f of xa, where f was exactly of the same form as what we have here. Now I've got a problem because this doesn't really look anything like this, okay? All right, most of what I've done up to this point is easy, okay? This is not so easy because here comes that generator again. We're going to use the fact that we know that expressions like this are martingales, and we have to very cleverly find the right f so we get a martingale that does everything we want it to do. And you can in fact find, I've called it h rather than f, sorry about that. You can in fact find an h, okay, there it is, such that if you apply the generator to it and use the fact that this is a martingale, what you discover is that this object here is a martingale. This term here is divided by n. That's going to go to 0. That will go to 0. But still, when I apply the generator to it, I pick up these factors of n. Okay? So even though this is normalized by 1 over n, hidden in the generator is a factor of n which cancels the 1 over n. And if you put all these things together, you get this identity, okay? Where this is a martingale, that's the first one. That's just this is the martingale that comes from the centered Poisson processes, okay? And this is the martingale that comes through this crazy calculation. Now there's something wonderful called the martingale central limit theorem that tells us that if we can compute the limit of what's called the quadratic variation, okay, you take your process, you take a bunch of, you look at little increments of your process, you square those increments, and you take the limit as the mesh that you've divided things up by, converges to 0, that gives you the quadratic variation. For the kinds of jump processes we're working with, it's actually reasonably easy to compute the quadratic variation from the process, but you can sort of see things are getting really ugly here. But this is easy to write down. You've got the once you've got this mn2, which is the real pain in this argument, once you've got the mn2, it's easy to write down the quadratic variation. Then you use the fact that you know a law of large numbers for the x and a, and lo and behold, you can actually prove that this converges to this gigantic mess here. Okay? And what does that tell us? That tells us that this quantity here, this scale, this rescaled difference, looks exactly like the classical result for centered concentrations. This thing here will converge, and if you look at it, this is linear noise, right? Here's a W run on some time scale. This is deterministic. Here is a familiar looking object. And so this is a linear noise approximation to the x and a, okay, where this sigma squared, this integral of sigma squared is, this integral of sigma squared is this whole mess here, okay? But that is the central limit theorem that goes with this business. And my leader says it's time for me. Who knows how long I can run on if I don't stop. If he doesn't stop me, I will in fact quit.
We have time for a question. Jim, do you want to set up while...
So your derivation of the material kinetics from Markov processes, that's cute. I've never seen that before. But there was one step in it that I didn't quite follow, so that you have a sequence of measures. Can you give me some, maybe some physical intuition as to what that means?
Okay. In the world of limit theorems and probability, there's something called the Prof theorem, and it involves a notion of tightness. Okay? The intuition is this. Think of a probability distribution as a big sand pile. Okay? And I've got a sequence of these sand piles. Okay? And so these sand piles are moving around. Okay? But I know I can find a nice box, okay, in which almost all of the sand is. Okay, there's only, say, 1/10 of 1% outside of this box. Now these little sand particles are moving around, and they have to have a limit point. You're moving around inside this box, elementary topology or something like that. They've got to have a limit point. Well, that notion of they've got to have a limit point applies to the whole sand pile. It's got to converge to something, okay? All right, and that's the general idea, okay? In the particular case I'm looking at, where you've got these time-dependent, these space-time measures, in this case, if you look at the probability of being equal to k, okay, as a function of time, that's just a nice continuous function of time, and for each k, and these continuous functions don't wiggle around too much, and you could, for each of those continuous functions, you could pick out a sequence, you could pick out a subsequence along which they converge, and then a further subsequence in which the next one converges, and so on. So in this case, you can see that there will be some subsequence of n's along which these gamma n's must converge. Okay, if you want to look at it, we can draw more pictures offline here. If that's
okay.
Okay, you ready to go?
Let's thank Tom again.